And now for your chapter of medical imaging is just mainly on you studying the 4 different technologies for imaging. Let's just say when you're sick and you want to do an imaging of your internal body structure, you have to go through an X-ray, you have to go through a CT scan, you have to go through an MRI, or you have to go through ultrasound. So this chapter here, medical imaging, talks about what are the different technologies that you use to do an imaging of your internal body structure. So you will learn about 4 main technologies. The first one is X-ray. The second one is CT scan. The third one is ultrasound. Then the fourth one is MRI. CT scan and MRI will be quite short. Now, but X-ray and ultrasound will be a bit long. Okay, so let's just start with the first one, which is X-ray. Okay, now you all know what an X-ray actually is. You know that if you want to scan, let's just say you have a broken bone, and you say you want to find out which particular part of the bone is broken, you do an X-ray, right? So most commonly, you know that you will do an X-ray to see what is happened to your bone. Okay, so before we go through that, you need to first understand this part first. Now, X-ray is actually your EM radiation. Because you remember this part from your AS physics. Remember that in your AS physics, when we say EM radiation, if you're talking about the EM radiation spectrum, there are actually a few types of waves. You have radio waves, microwaves, infrared, ultraviolet, sorry, imaging motions, sorry. You have visible light, ultraviolet, X-ray, and then gamma rays, right? And then after that, we will tell you that for these waves that are inside your EM radiation, there's a certain range of wavelength to them. This is 10 power 3, 10 power 0, 10 power minus 3, 10 power minus 6, 10 power minus 7, 10 power minus 9, 10 power minus 12, and this is 10 power minus 15, right? So specifically when you're talking about X-ray you know is at this region here. Okay, X-ray is here. This one, if you have EM radiation whose wavelength is between 10 power minus 9 to 10 power minus 12 wave meter, that one is actually your X-ray. You know that if you go from left to right, your wavelength will decrease, but your frequency will increase. Okay, so the thing here is that X-ray, you need to first understand that is EM radiation. And then from last chapter, quantum physics, you learned that when you're talking about EM radiation can be thought of as waves. It can also be thought of as photons, or rather particles called photons, right? So here we make use of that knowledge that EM radiation can be thought of as particles called photons. All right. So how do we generate X-ray in the first place before we do an imaging of your internal body structure? When we want to generate X-ray, we have to make use of something called an X-ray tube. Okay. Now, an X-ray tube in its simplest form just looks like this. There's a particular circuit here where you have a filament, a core of filament. And then there's another part of the circuit, there's another part of your X-ray tube that consists of a metal part, core and a metal part. So what we'll do is that we will charge the metal part so that it has a positive, and then we will charge the filaments so that it has a negative. Okay, so that there's a potential difference between these two parts. Okay, so when you want to generate an X-ray, what we'll first do is this. We will connect that filament, that core of filament, to a power supply. We will switch the current on so that current is flowing through the circuit here, and it flows through the filament, the core of filament. As current flows through the core of filament, that filament will heat up and it will start to emit electrons. Okay. Now the electrons that are emitted, once they are emitted, because they are emitted inside a potential difference, a region with potential difference. Remember just now I told you here your anode is positively charged, your kappa here is negatively charged, so that there's a potential difference between them. So when your current runs through your filament coil here, and you get electrons being emitted, what will happen then is that the PV here will accelerate that electron from here to here. Okay, from the cathode towards the anode. You can think of the cathode as repelling the negative electron, and the anode actually attracting the electron. So what you end up with is that the electrons are accelerated from left to right. The electrons will actually gain speed here. They will actually have increase in kinetic energy. Okay. Now, once your electron speeds up, it will eventually heat up. Once your electron speeds up, it will eventually hit the anode. Okay, there's a metal part here called an anode here. So the thing is that once your electron speeds up, it will hit the anode, and then once it hits the anode or strikes the anode, it will now slow down. Okay, so what is actually happening here is that whatever kinetic energy that your electron has here is now being lost as a result of the collision with the anode here. It is losing Ke, and whatever Ke is lost right now is actually converted to photon energy. Okay, so it is whatever Ke that you lost here that is converted to photons. That photon actually is your X-ray photons. Okay, remember just now I told you that when you're talking about X-ray being part of EM radiation, you can think of EM radiation as being particles also, correct? So the thing is that once your electron speeds up and hits the anode, it slows down, it loses energy. Whatever energy is lost is converted to photons here. And that photon energy that you have is equivalent to the photons, is having energy equivalent to X-rays. Okay, because you see here, when you're talking about energy of photon, E is equals to hc over lambda, right? You understood that for X-rays, there is a certain range of wavelengths for X-rays between 10 power minus 9 to 10 power minus 12. So this also tells you that your energy of your X-ray photons will have a certain range. It just so happens that once your electrons are decelerated or slowed down, whatever Ke lost, the amount of energy lost has energy equivalent to energy of X-rays. Okay, so you get X-ray photons here. Alright, so this is where you get your X-ray beam. If you want to do an imaging of your body, you will have a person standing here, and then you have an X-ray film here. So the X-ray will pass through the person, you will darken the X-ray film behind, and you get your X-ray image. Okay, but we won't go through the imaging part first. We just go through the part how you produce an X-ray first. Alright, so this is how you produce your X-ray beam in the first place. Okay, now when your electrons hit the anode and slow down, they all won't slow down by the same amount. Some of them will slow down a lot, some of them will slow down a little, some of them will stop completely upon hitting the anode. So what we'll say here is that the electrons actually undergo a range of decelerations. So when you undergo a range of decelerations, you will have a range of kinetic energy loss. Hence, you will have a range of photon energies emitted. Okay, and hence a range of wavelength. So as I mentioned to you, whatever range of energy and range of wavelengths that you have here will tend to correspond to that of X-ray. Okay. Now, from there, we can make some further analysis where we say that if we are talking about an electron that is stopped in a single collision, the electrons that are stopped in a single collision results in photon with the highest energy. Okay, here it was mentioned that the X-ray photons come out with a range of energies, but the one with the largest energy, the photon with the largest energy, will actually come from electron that has been stopped completely in a single collision. Okay, so electron that is stopped in a single collision will result in photons with highest energy. This is how you get the most energetic photon. This is how you get the maximum energy of your X-ray beam. Okay, so if you're talking about what happens to the electron that is being stopped in a single collision, you can still say this: whatever kinetic energy that is lost is equal to the energy of the photon produced. Now, this expression delta K can be changed to something else. You recognize that there is an isolated charge here, which is electron, and you also recognize that there is a potential difference between here and here. When you have potential difference, you have electric field. So here in the electric field chapter, we mentioned to you before, if you are trying to find out what is the work done on an isolated charge inside an electric field, the equation is normally W equals to Q delta V, isn't it? What we mentioned that time was that work done on an isolated charge is equals to Q delta V. Okay, charge times the potential difference. So here, the work that you do goes into changing the kinetic energy of the charge. Here, I'm just doing it the other way around. I'm saying that the kinetic energy change that the charge experiences is a result of the work that is being done on the isolated charge. So this one can be changed to this, which in turn gives you the energy of the photon. Now from here, you can see this. If you were to change your tube voltage, this delta V here is actually the potential difference between your cathode and your anode. It's actually known as your tube voltage. Okay, so what you can see from here is this. If you were to increase your tube voltage, you will cause a higher energy of your photon. All right. So the idea is that if you wanted to get an X-ray with even larger energy, with even more energies, what you will do is this: you will increase the tube voltage, because from here you can see that the energy of the X-ray photons that you get is actually dependent on the tube voltage. If you increase your voltage, you will get higher photon energy. If you decrease your voltage, you will get lower photon energy. Okay, so this is one thing. And then after that, when you're talking about energy of your X-ray or the photon energy of your X-ray, the higher the photon energy of the X-ray or the higher the energy of the X-ray, the higher is penetration power. Okay, if you want your X-ray to be able to penetrate deep into a particular medium, you need the energy to be high. Okay, so higher photon energy here results in higher penetration power of your X-ray beam. Okay, now, and when we're talking about high penetration power, sometimes we call those X-rays as being hard X-rays. If your X-ray has no penetration power, we call those soft X-rays. So sometimes you see in your questions, they'll tell you it's a hard X-ray, it's a soft X-ray. Just know that if they say that it's a hard X-ray, it means that it has high penetration power, high energy. If it's a soft X-ray, that means it has no penetration power, low energy. Okay. Then after that, there's one part here. Now, soft X-rays in themselves, the ones with low penetration power, they actually will be absorbed completely by your body. Okay, if here is your X-ray beam, and then after that here is your person whose bone you want to do an X-ray of, the soft X-rays, once it goes to a person's body, the X-rays here contain both soft and hard X-rays. Okay, whatever X-ray beams you produce normally have both soft and hard X-rays together. Okay, because your electrons undergo a range of deceleration, so you would have a range of photon energies. Some of them is very low, giving you soft X-rays. Some of them is very high, giving you hard X-rays. So you cannot really control it. So the thing is that for the X-rays that are incident on your body, soft X-rays are absorbed completely by your body and won't contribute to your X-ray image here. Okay, so they actually increase radiation dosage unnecessarily. Okay, your X-ray film here is where you get your image. Your soft X-rays plays no part in producing an image on the X-ray film. It was just completely absorbed by your body. Okay, so it doesn't contribute to your image, and at the same time it increases your radiation dosage for no apparent reason. So this one here is a health risk. So if you want to get rid of that soft X-ray, since it's not really useful here in any way, what we'll tell you is that you will tend to use what we call an aluminum filter. Okay, where would you put your aluminum filter is somewhere around here. When your X-ray is going from here to here towards the person whose X-ray you want to do, you put an aluminum filter before the X-ray hits the person. Okay, the aluminum filter here will actually now absorb all the soft X-rays, allowing only the hard X-rays to pass through. So what comes out of your aluminum filter is just the hard X-rays. The aluminum filter will absorb the soft X-ray. So in this way, you avoid this thing from happening. Okay, so that one is all right. Okay, so now, just now that I mentioned that if you want to get a higher energy of your X-ray, you need to increase your tube voltage. So what is then the effect if I increase tube current? In this diagram here, I indicated to you that the potential difference between the cathode and anode is actually your tube voltage, and that one has an effect on your photon energies of the X-rays that you produce. What can you then say about the tube current here? Now, your tube voltage and tube current are two different things. They are not referring to the same part in your tube. Okay, tube voltage is this, tube current is this. Now, when you want to find out what is the effect of tube current on your production of X-rays, we will just tell you this. If you increase your tube current, more current flows here will only cause more number of electrons emitted. Okay, so more number of electrons emitted means more electrons will hit the anode and slow down, which in turn then causes more photons to be emitted. Okay, here tube current, if you were to increase the tube current, you're only going to cause more electrons emitted, which in turn causes more photons to be produced, more X-ray photons to be produced. So when you have more photons produced, more X-ray photons produced, this has the effect of increasing the intensity of your X-ray beam. Okay, so because you see last lesson under the quantum physics chapter, we mentioned intensity as total energy over time over area, right? Total energy being number of photons multiplied by photon energy. So intensity being n times E over T times A. So if you have more photons emitted, your n has increased. Your n has increased, your intensity has increased. Now your energy itself, if you're still using the same tube voltage while increasing the current, the energy of the photons that you produce, the maximum energy that you get is still unchanged. Okay, so here increasing the intensity of increasing your tube current here doesn't have any effect on your photon energy. Okay, it only has the effect of increasing the intensity of your X-ray beam. If you want to change the energy of your X-ray beam, you have to change the tube voltage. Okay, so just be careful of these differences, because your questions would like to ask you what happens if you change the tube current, what happens when you change the tube voltage. All right, so that part is okay. So as I mentioned, increase in tube voltage causes increase in photon energy, hence increase in penetration power. All right, so that part is okay. Then there is one part that I need to move on to also. This one I won't have to refer to your notes that I gave you last time. Okay, just now I mentioned to you that when your electrons hit the anode, they will undergo a range of decelerations. They will then give you a range of photon energies. So if you're talking about having a range of photon energies, this also means that you will have a range of wavelengths, because you know that energy of a photon is equals to hf, which is then also equals to hc over lambda. All right, so it is understood that when you have a range of photon energies, you will have a range of wavelengths. So if you were to analyze the wavelengths of the X-ray photons produced, you will normally get something like this. If you refer to the medical imaging notes that I gave to you some time back, refer to page 2, what we will tell you is that if you were to analyze the X-ray photons produced from your X-ray tube and you were to try and plot a graph of, say, intensity versus wavelength, in general, you will get a shape like this. Okay? In general, you will get a shape like this. Okay? So this one here is like this. You get a shape like this. Alright? Now, this intensity here can be thought of as representing the number of photons. Because when I told you I is equals to n times E over T times A, right? I can be thought of as representing the number of X-ray photons you produce. And then this lambda here, you know that E is equals to hc over lambda. The lambda here can be thought of as representing energy. Okay, can be thought of as representing energy. Intensity represents the number of photons. Energy, wavelength here representing the energy of the photons produced. Okay. Now, in general, you will tend to get a distribution that looks like this. Some of your questions in your paper will ask you, why is it that when your X-ray photons are produced, they come with a range of wavelengths from here to here. So as I mentioned to you, part of the reason was simply because when your electrons slow down or decelerate, they do so by different amounts. Some will slow down a lot, some will slow down a little, some will just stop completely. Hence, you will have different photon energies produced. And when you have different photon energies, obviously you will have different wavelengths of photons produced. Okay, so this is one common question they would like to ask you. Why do you have a continuous distribution of wavelengths? All right. And then another thing here is this. They will also like to ask you, why is there a sharp cutoff at short wavelength? Now, before we go to that, if you look at this shape of the graph here, the most energetic photon, where do you suppose it will be? Is it on the left-hand side or the right-hand side? If you look at the equation, E is equals to hc over lambda. When lambda is small, that means your E is big. So from this relation here, you see your most energetic photon is actually here. This is where your most energetic photon is. This part here is where you have your least energetic photon. Okay, the weaker photons is here. The weaker X-rays is here. The stronger X-rays are here. Okay, so they ask you, why is there a sharp cutoff at short wavelength? When they ask you sharp cutoff, it kind of refers to this. You see, if you get something like this, and then say you get something like this is, you compare something like this versus something like this. You see how the cutoff occurs. Cutoff here simply means it cutting the x-axis. Okay, the cutoff here means how it cuts the x-axis. All right, the cutoff here means the part where it cuts the x-axis. Right, the cutoff here means cutting the x-axis. Now, when your graph cuts the x-axis, it can do so in two ways. This one here, you see it gradually drops before it cuts, right? This one, it drops rapidly before it cuts, right? This one here is, you can think of this as gentle cut off. This one is, how to say, I don't know what is the proper word for it. This one seems to be a gentle cut off. When we say sharp cut off, this is what we mean sharp cut off. It immediately, it doesn't, the sharp cut off here is like when you see the gradients suddenly drops like that instead of gradually decreasing. Okay, this one you see when it wants to cut, it does so in a very gradual manner. Okay, maybe this one I don't use the word gentle cut off. This one I call it gradual cut off. Okay, the proper term is gradual. Okay. See, this is what we call gradual cut off. It does so very, very slowly, leading to it leading to the cutoff. But sharp cutoff is this. It doesn't do so very slowly. It just almost immediately drop and cut the x-axis. Okay. So the question here is, why does it just suddenly cut off like this? You can think of the sharp cutoff here as actually being due to the fact that at this point, the cutoff here is actually due to the electron being stopped in a single collision to give out all its energy to produce an X-ray photon. Okay, that is what the sharp cutoff there. That is how the sharp cutoff there is produced. Your question papers would like to ask you, why is there always a sharp cutoff at the diagram? It's because an electron will give out all its energy to produce an X-ray photon when stopped in a single collision here. Okay, that's what the sharp cutoff means. It suddenly just stops. There's suddenly a stop in the wavelength. Another way to look at it is this time. The sharp cutoff here could also mean that, you see, if you look at your graph, your wavelength gradually increase to a higher and higher value. Your wavelength, if you go towards the left, it doesn't gradually decrease to a lower and lower value. It just suddenly stops. Some people would think the sharp cutoff as that. Okay, the cutoff here means it doesn't keep going to a lower value. It just suddenly stops. It cuts off there, just like that, without warning. Okay, for some people, when you ask them what does a sharp cutoff mean, it means that in your case, if you go from right to left, the lambda value doesn't keep dropping. It just suddenly stops. It just suddenly cuts off. That is what some people will view the cutoff as being. Some people view it in terms of the gradient. Some people will view it in terms of the value. It doesn't just keep on decreasing. Instead, it just stops suddenly. Why did it just suddenly stop? Why did the wavelength value just suddenly stop? The reason is because at this point here, your X-ray was stopped in a single collision, giving out all its photon energy. So if your electrons have already been stopped in a single collision, you cannot expect to produce any more photons with lower wavelength. Okay, because you know that your energy or your photon is related to your wavelength. If your photon is already being stopped in a single collision, this is the lowest it will ever go for your wavelength. This is the highest energy of your photon you will ever get. This is the lowest wavelength you will ever get. You will not get anything more after that. All right. So for some people, they think of cutoff as being that, and they explain it this way. Okay, your cutoff being because your X-ray is stopped in a single collision to produce an X-ray once the electron gives out all of its energy. Okay, so that is one part for the sharp cutoff. All right, then if you look at the other one, whatever you have here, the ones in the square boxes, but it's not colored, it's not really that important. It's just meant to show you certain relations there. All right, the important relation I already showed you here. This one will tell you if you're talking about the most energetic photon, what happens. All right. Then if you look a bit further down to, before we go to that, this one here, they tell you the smaller your voltage, the smaller your value of lambda mean, the smaller the value of your wavelength. Now, if you look back at your graph here, there's actually two different graphs, right? The red colored graph and the green colored graph. Now, your green colored graph is for a specific tube voltage that you use. You still get that same general shape, which is like this, okay? What happens when you use a higher tube voltage at V2? Now, the understanding is that when you use a higher tube voltage, as I mentioned to you, when you use a higher tube voltage, you're going to get a larger photon energy because it was mentioned that Q delta V is equals to E, right? You use a larger tube voltage, you're going to get a larger E. When you get a larger E, you're going to get a smaller wavelength. So the effect of you having a larger tube voltage will mean you get a more energetic photon. Your wavelength will be smaller. So you increasing your tube voltage will cause you to have a smaller wavelength than before. So your new shape looks like this. That's how this shape came about. All right. That's what this statement here is referring to. The higher your voltage, the smaller the value of your smallest wavelength. All right. Okay. Now the other things that we will also ask you is this. Why is it that on your graph, there are normally a series of peaks? Now, in general, your graph shape looks like this, but you notice that there are certain peaks there, right? You notice that there are certain peaks here, or certain peaks here, right? When you look at your own graph here on your notes, you notice that the peaks are occurring here, here, and also here, right? Even though you change the tube voltage, the peaks are occurring at the same wavelength. Now, before I explain this part here, let me just explain this part. Now, how do you get the peaks in the first place? Now, the thing that we will tell you is this: when your electrons hit the anode, what happened is that the electrons that came from here to here, it actually knocked off the electron of the atoms in your anode. Your anode here, you can think of it as consisting of other atoms, where maybe I shouldn't draw so much. Okay, you can think of your anode here as being consisting of atoms, where it has a positive nucleus and electrons orbiting around the nucleus. Okay, your anode here is a solid metal structure, so you know it consists of atoms. And when you're talking about atoms, you know that it has a positive nucleus and electrons orbiting around it. So the thing here that we will say is that once you accelerate your electrons from here to here, under some cases, your electrons that were accelerated will actually knock off the electrons that are already orbiting around the nucleus of your anode atom. Alright, so once your electron is knocked off, you now suddenly have a vacancy in your shell. Okay, originally there was electron orbiting, but because another electron came in like this, it was moving at high speed, it knocked off the electron, and then suddenly the electron being knocked off here will cause a vacancy of electron here. Okay, that is what is being shown here, right? Consider that this is the atom of one anode. Okay, one anode atom. All right, consider that this is the atom of one anode atom. This is your positive nucleus. This concentric lines here represent your electron shells. So say for example, your electron that was accelerated, it moved, and then it knocked off 3 electrons from your inner shell. 3 electrons were knocked off from your inner shell. Okay, this one you can think of it as electrons knocked off from collision with other electrons. Okay, so once you accelerate the electrons from the cathode to the anode, it could come to a case where the initial electrons will knock off as a collision with the electrons that were accelerated. So now what you have are vacancies inside the inner shell. And in chemistry, you learn that you cannot have any particular vacancy inside your inner shell of an atom. They must be completely filled in the first place. So the thing is that your inner shell now has some inner shell vacancies. This vacancy cannot remain here. They must be filled. What will happen then is that the electrons in the other shells, other outermost shell, will now drop down to fill the vacancies. Okay? Initially, you have the vacancy here as a result of collision with other electrons. So this vacancy here, the electrons in the other shells will now fall in to fill the vacancy. And in your quantum physics, you learn what happens when electrons change energy levels, right? We mentioned that if electron jump from lower energy level to higher energy level, it will absorb photons. But conversely, if an electron drops down from a higher energy level to a lower energy level, you will emit photons, right? So here, the first electron jumps from this shell to this shell, is dropping to a lower energy level. The same can be said for this as well as this, right? So when they are dropping down from a higher energy level to a lower energy level, you understood that there will be emission of photons. So this one drop down got photons. This one drop down, it will emit photons. This one drops down, it will also emit photons. Okay, these photons here are additional photons, X-ray photons. They are additional X-ray photons, which adds up to here, here, and here. Okay, so the reason why you have the spikes here is because it's showing you the presence of additional X-ray photons. Okay, so your additional X-ray photons came about because your electrons inside your inner shell will knock off. So electrons drop back down, and when they drop down, they emit new additional photons, which is adding to your existing X-ray photons. Okay, that explains to you the presence of the peaks here. Okay. Now, if you look at the other graph, the one with the higher tube voltage, you notice that the peaks also occur at exactly the same wavelength. All right. Now, the reasoning why the peaks occur at exactly the same wavelength is because in your case here, even if you change your tube voltage to a higher value, your anode, you did not change. You did not change the material. You did not change the element type. So your electron configuration will still remain the same. The electron energy levels of the atoms will still remain the same. So even at higher tube voltage, when your electrons knocks off the electron in the innermost shell, your electron configuration is still the same, your electron energy levels is still the same. So when your electrons on the higher shell drop down to the lower shell, you're still going through the same energy level, hence you're still going to get photons of the same energy. All right, so you're still going to have additional photons giving you this spike, but they will be same value as when you use the lower voltage. Okay, because here you're using the same element. Same element means same electron configuration, same electron energy levels. So you're always getting back photons with exactly the same energy, same wavelength. Okay, so hence this one is basically telling you that. All right, the initial vacancies are refilled by 3 electrons. Additional X-ray photons are emitted, adding to the X-ray photons already produced by the deceleration of the electrons. Okay. So the dimension of intensity, this one I explained already. The dimension of the hardness of the X-ray beam has also been explained too. Okay. Then I move to the actual process of you producing an X-ray image. Okay, this part covers production of X-ray beam. The next one here will cover the production of an X-ray image. All right. Now, you all know an X-ray image as something similar to this one. Okay, a typical X-ray image will look something like this, right? Okay, the X-ray image, the X-ray field is normally dark in color with some white regions, right? Okay, now before we go to that, your X-ray film, you need to understand that your X-ray film is originally black or white. Okay, maybe it's better if I just look at this one first. Now, before you develop any image on your X-ray film, the X-ray film, when undeveloped, X-ray film, when undeveloped, meaning to say no image yet, is completely white in color. Okay, because some people tend to mistake it the other way around. They think that the X-ray film is completely black in color. It's just that when the X-ray hits the X-ray film, it starts to whiten. It's not doing it. That's not true. Okay, your X-ray film is originally white, is completely white in the first place. It's just that when your X-ray hits your film, that it darkens. Okay, so your X-ray film when undeveloped no emission yet is completely white. It darkens when X-ray is incident on it. Okay, so this is the first thing you need to know first when you're talking about X-ray film. It's originally white, originally completely white. It will only start to darken once you have X-ray incident on it. Okay, that's how you produce an X-ray film in the X-ray image in the first place. So, how do you go and produce an image of the X-ray of a certain body? Now, this part here you understood is actually referring to your X-ray tube. It tells you how an X-ray beam is produced. If you want to produce an X-ray image, what you do is that you direct the X-ray beam that is produced towards the person or object that you want to do an image of. Okay, so the idea is that you want to let the X-ray beam pass through the person and then darken an X-ray film behind that person. Okay, so you direct your X-ray from your X-ray beam towards the person. You place an X-ray film behind that person. The idea is that you want the X-ray film, the X-ray, to pass through the person and darken the film behind that person. Okay, so in general, if this one here is the outline of a person with his skeleton and the blue outline here being, say, his flesh, if you were to produce an X-ray image of that person here, the ideal image would be this one, okay, where the X-ray film is completely black throughout and then only the bone region is completely white. So how did it produce this image in the first place? You can think of it as this. Now when your X-ray beams pass through, you understood that X-rays can be absorbed by certain mediums. Okay, some medium will absorb a lot of the X-ray, some medium will absorb a little of the X-ray, some medium will absorb completely the X-ray. So you consider, say in your case right now, bone and muscle. Okay, when you're talking about bone, bone will absorb the X-ray completely. Okay, muscle will absorb a little, right? Okay, will absorb a little. So for the bone, when we see that bone absorbs the X-ray completely, what we'll then be able to deduce is that no X-ray will be incident on bone behind, sorry, not this one, sorry, one mistake. If your bone absorbs the X-ray completely, what this means is that no X-ray will be incident on X-ray film behind the bone. Okay, but if you're talking about muscle now, where we tell you that it absorbs only little, then we will say that there will be X-ray incident on the film, incident on X-ray film behind muscle. Okay, that is the basic understanding here. If you're just talking about muscle and bone, bone will absorb all the X-ray, so none of the X-ray will be incident on the X-ray film behind the bone. But you're talking about muscle, muscle will absorb only a little, so there will be still X-ray incident on the X-ray film behind the muscle. Now, it's because of these two facts here that you get this image. You can imagine that, say, for the X-ray that did not pass through anything, it will hit the film, it will darken it. For the X-ray that passes through just your muscle, only a little has been absorbed, there will still be some that manage to pass through and hit the X-ray field, so darkening the field. But for the case where you have the X-rays that is incident on the bone, that pass through the bone, was completely absorbed, say for example here, right, the X-ray that passed through and hit your bone, the bone will absorb all your X-ray, so none of it will pass through it and hit the X-ray field. If your X-ray is hitting your bone absorbs all the X-ray. Behind your bone, there'll be no X-ray left. So nothing will actually come out to darken the field. So this part here will be completely white, as you can see here. Okay, so this is how actually your X-ray image is produced. Alright, it relies on darkening of the film, and when you say that it darkens the film, it relies on the film being darkened by different amounts to produce your image. Okay, so the summary was just basically this. Your X-ray image is produced when different regions of the film darken when X-ray is incident on it. Different regions of your body will absorb X-ray differently, resulting in different intensities of X-ray on the film. Okay, so that's how you get those regions where some of them is white, some of them is black, and then giving you that image there. All right. Okay, then after that, there's one thing I should mention also. Now, when you're talking about using your X-ray, you need to make sure that your X-ray is not too strong, not too weak. In other words, not too soft, not too hard. If say, for example, your X-ray is too soft, it's very weak, what will that mean is that if it hits your bone, it will be absorbed completely. If it hits your muscle, it will also be absorbed completely. So nothing will actually pass through the muscle and darken the X-ray film. So at the end of the day, what you see is that for the X-ray film you're only seeing the outline of the person because everything was absorbed by the person. Both muscle and bone absorbed everything, so nothing came out behind. So what you see is just the outline of the person. But if your X-ray is too hard, okay, that will mean that it's too strong to the point that even your bone cannot absorb all the X-ray. There will still be X-ray that pass right through your bone behind it, darkening the film. So what you then see is that your X-ray is completely black. Okay, this is the effect of having X-ray too strong. Okay, so if you want to get a proper image like this one, you need to make sure that it is not too soft, not too hard, something in between. Only then can you get a proper image like this. All right, so this is how you get your X-ray film. All right, X-ray image, sorry. Now, when you get your X-ray image, we will also ask you to judge the quality of the X-ray image. Now, if you want to judge the quality of your X-ray image, we will normally tell you about two things: sharpness of the image as well as contrast of the image. Now, if you want to talk about sharpness of image, the easiest thing I can tell you is, okay, in the first place, we tell you sharpness is actually the ease with which the edges of a structure can be determined. Okay, how do you view sharpness is this? When you take a photo using your smartphone, the moment you press the snap picture button, if at that moment your hand was shaking or your hand was moving, you will notice that the picture you get will be blurry, isn't it? You notice that whatever object that you're taking will tend to have double or triple lines around its outline. If say you're taking a picture of a person's face, if your hand was moving or shaking at the moment you press the snap picture button, the person's face you see will be very blurry, right? You notice that around the person's face there'll be like 2 or 3 different lines instead of a single line showing the outline of the person's face. That is what we call as sharpness, right? The ease with which the edges of the structure can be determined. When something is sharp, you can clearly see the outline of the object or the person. It won't be blurry. You won't see like there's 2 or 3 different lines around the outline of the person. Okay, that is what sharpness actually means. And then after that, there is also something called contrast. Contrast is just simply the difference in degree of blackening between different regions. Now, what do we mean by that? This one will be easier to see by looking at the notes, especially this part. Okay, this is a chest X-ray image. Okay, they give you two examples here. One example is poor contrast. One example is good contrast. In your case here, when you look at this one here, because contrast is defined as the difference in the degree of blackening of different structures in the image, when you say you have good contrast, you can clearly see the black and whites in the image, right? You can, like in this image here, you see certain regions are clearly black, certain regions are clearly white, right? You compare to this image here, the blacks and whites regions aren't really that different from each other. But when you look at this one here, the black and white regions are very different from each other. You can clearly see which one is black, which region is black, which region is white. This one here, you don't know. It's a bit dim, it's a bit faint, right? You don't know which part is clearly black, which part is clearly white. So this is what we call example of poor contrast. And then this one is example of good contrast. Okay? In other words, you can clearly see the black, you can clearly see the white. Alright? So that part is talking to you about the quality of your X-ray image. Then the last thing that I should kind of mention is this one. Now your sharpness will be affected by your X-ray image sharpness can be affected by a few factors. It can be affected by your anode size, it can be affected by your aperture size, and it can be affected by any scattering of your X-ray beam. Now, sharpness is affected by anode size. We will tell you the smaller your anode size, the smaller your partial shadow. The anode that we're talking about here is this one, the anode here, okay? The one where you expect X-ray to hit and then after that produce a X-ray beam, okay? So the thing here is that if we tell you that the anode that you use here is very large, you're not going to get a very sharp image. You need to use a small anode so that you get a very sharp image. You can think of it as being similar to something like this. This one you have to refer to page 5. Okay. This one tells you what is the effect of anode size on the X-ray image. Say this one is your anode now. Okay. And then this one here is the object that you want to do an imaging. So you understood that if electrons hit this anode, you're gonna get X-ray beams in this direction. So it passes through this object here and you will produce an image on the X-ray film here. So the thing here is that if your anode size is small, we will tell you that your X-ray image that you get would have a small region of partial shadow, making it sharp. Okay. If on the other hand your anode size is large, as evidenced by here, when you try to produce your image of the object, you're going to have a large partial shadow. Okay. When you look at this one will be sharper. This one will be less sharp. Now, the concept of partial shadow, you can think of it as this. You know, sometimes when you walk outside under the street light or someplace with some very weird lighting, you notice that around your shadow, there's another secondary shadow. That is what we call as your partial shadow. Sometimes when you walk through the streets under lights at different angles, you will notice that around your main shadow, there's another secondary shadow, right? That is what we call as your partial shadow. If you can see a very large region of your partial shadow around your main shadow, like this one here, this is not considered to be a sharp image. But you see no partial shadow or very little partial shadow around your main shadow, that one is considered to be a sharp image because you can clearly see the outline of your object. Alright, so here, smaller anode size, smaller partial shadow, hence sharper image. Okay. And then the other one here is aperture size. We will tell you that the smaller your aperture size, the narrower your X-ray beam, hence the sharper it is. Now, aperture is just simply some plates which you arrange to form an opening in the middle. If you want your opening to be smaller, you just arrange the plate so that the opening is smaller. If you want your opening to be larger, then you just arrange the plate so that your opening is larger. Now, the aperture here actually will control the size of your X-ray beam. All right. Wait, let me just erase this one. Okay. Now, the aperture actually controls, rather than saying control, it controls the size or width of X-ray beam. Okay. Now, in general, we say that the narrower the X-ray beam, the sharper the image. Okay. Aperture controls the size or width of your X-ray beam. In general, if your X-ray beam is narrower, the image will be sharper. You can relate this concept to what you see here. You see your anode size being small and your anode size being big. You can try and compare the size or width of your X-ray beam. In your case here, if your anode size is small, you notice that maybe your X-ray beam is this width. Okay, this one is narrow, right? Narrow X-ray beam, which in turn gives you small partial shadow, hence sharp image. But if your anode size is large, your X-ray beam produced is wide. This one is wide X-ray beam. So when it hits an object, you get a large partial shadow, so it's less sharp, isn't it? So the width here actually plays an important part in sharpness. Okay, so actually when you're talking about the anode size and the size of the aperture, which in turn affects sharpness, these two actually affects the size or width of your X-ray beam. If you're able to make it in such a way that the X-ray beam is narrow, you're going to get a sharp image. So for the case of anode size, if you want your X-ray beam to be narrow, you use small anode size. In the case of an aperture, if you want your X-ray beam to be narrow, you use aperture to purposely limit the size of your X-ray beam produced. Okay. Now where you want to put your aperture is here. If you're talking about your aperture is here. All right. Your electrons hit your anode, you produce your X-ray beam. Before your X-ray beam hits the person whose X-ray image you want to take, you narrow the X-ray beam by using the aperture here, by placing the aperture here. Okay. Then after that, you will pass through the person and produce an image with small partial shadow, so your image is sharper. Okay. Your aluminum filter here is the one from the previous screenshot. The aluminum filter here I mentioned to you is meant to absorb any soft X-ray because they don't have any purpose here. They only increase your radiation dosage unnecessarily. Okay, so that part is fine. Okay, then the last factor that will affect your sharpness is the scattering of your X-ray beam. Now, when we say scattering of your X-ray beam, it means this one. This is the last one of the last few examples. Now you look at this one here. This is the object that you're trying to do to produce an image of. Okay, this one, the purple region here is your bone. The red outline here is your muscle. If you try to produce an image, X-ray image of this thing here, you expect only to see this one, where the rest of the regions are darkened, right? This is what you expect to see. Okay, if you produce an X-ray image of this thing here, on your X-ray film, you expect to see everything is black except the region behind the bone. You only expect to see this, right? Now, when your X-ray beam is passing through your medium, we will tell you that your X-ray will actually scatter. As it passes through your medium, because of effects like diffraction, it will actually change direction. Okay, so your X-ray beam, as it moves through your medium, it will actually deflect and change direction. So the effect of that is this. If you look at the few beams that have deflected or scattered here, this one here, by right, especially this one, you just look at this part here and this part here. By right, this region here should not have any X-ray to darken the region. It should be completely white, right? But if you have X-ray that deflect, that is scattering or deflectant, you can actually end up with some X-rays actually darkening this area where it should not be darkening. Okay, and likewise, this area here is where it should be incident on the X-ray film and darkening the film, right? If your X-ray is changing direction to another place, that means that X-ray is not hitting this place. It's not darkening this place where it should be. Okay, so your X-ray beam, if it deflects, what you will see is that it is darkening somewhere it should not be darkening. It is not darkening somewhere where it should be darkening. So as a result, your X-ray image that you get will not have good sharpness, or rather, it will also not have good contrast, because what's supposed to be black is not that black. What's supposed to be white is now not white. Okay, so that is what scattering of X-ray beam does. The darkening and lightening of the regions where they shouldn't by the X-rays. If you want to avoid that, what we'll say is that you will need to use a lead grid. Okay, when you use a lead grid, this is what happens. The lead grid is just simply a plate with a lot of slits, something like this. When you view it from the side, it looks like this. So the purpose of the lead grid here is to block off the X-rays that have scattered and to allow the X-rays that are still straight to pass through. You can see in this illustration here, X-rays that have actually scattered to where it shouldn't are now being blocked by the lead grid. But the X-rays that are not scattered, they're still moving in the same original straight line, they are allowed to pass through and produce the image as it should. Okay, so in this case here, if you want to prevent the effect of scattering of your X-ray beam, you have to put a lead grid. Now your lead grid will be put somewhere here after it has passed through your person and about to go to the X-ray film. Okay, so improvements to your X-ray image will be done here. Changing the anode size will be done here at the aperture, changing the width of the X-ray beam, and then the last one will be done here at the lead grid to prevent or block off all the scattered X-ray beams, allowing only the ones that are straight to pass through. Okay, so that much is clear.